Hello, everyone. I am Wong Dexter. You can call me Dexter. I am a research assistant professor from the Department of Biomedical Engineering at the Hong Kong Polytechnic University. I'm going to share some of my work to represent my academic breakthrough. So let me start. So this is the outline of my research work. Let me use a red point thinker. Yeah, here. So let me go. So this is the overview of my research field, and in the following, I will mainly include two topics. The first one is the fundamental to translational study, that is about the mechanomedicine, and also the second one, the biosensor for biomarker detection. Okay, let me start with the first one's background. So the first topic is about mechanical cues to influence cell behavior. The mechanotransduction is an important factor that can be changed into the chemical signal to regulate gene expression. And compared to the soluble factors, the mechanical transmission is fast and effective to govern the cell signaling. Also, the application of ECM-based mechanical stimulation can provide a biomimetic microenvironment to cells. So this physical linkage can mediate the focal adhesion formation and provide a platform for recruiting more signaling molecules that can control the cell proliferation and differentiation. So the mechanical property of biomaterial can modulate the integrin ligand binding dynamics to affect the intracellular signaling pathway and cell phase to the desired phenotypes. And this is very crucial for biomaterial and tissue engineering. However, previous studies failed to regulate the cell adhesion without changing the biochemical content that can affect the cellular events. To solve this problem, we designed a novel nano platform consisting of a monolayer of RGD-bearing magnetic nanoparticle conjugated to a substrate through a long and flexible polymer. We are the first reports to tune the local mechanical property by magnetic field. So without the magnetic field, the surface is soft while it is stiff with magnetic attraction. So we also define a critical threshold tether length that directly regulates the stem cell adhesion, spreading, and differentiation. So cancer stem cell is shown to be the cause of cancer recurrence. So therefore, we developing in vitro model to culture cancer stem cell can facilitate the drug screening for the treatment. But traditional method can be very costly and low efficiency. Our work here shows that this platform is cost effective to generate cancer stem cell spheroid with high malignancy in vitro and in vivo. So in overall, our platform is a good platform for cancer stem cell drug screening and can be easily imaged to visualize some markers that are important for mechanistic study. Apart from a static binding, RGD integrin binding can actually oscillate at a natural cycle, but no previous platform is available to study this mechanism. In contrast, our platform can achieve this outcome because the RGD bearing particle remain attached to the substrate while responds to oscillating magnetic field at different frequency. So in our finding, very surprisingly, our work shows that 0.1 Hz oscillation increased the chance of RGD integrin binding that promote the formation of focal adhesion and osteogenic differentiation. But these results are not found in other frequency. Therefore, we established an important parameter that synchronizing with the natural oscillating frequency of ligand receptor can promote the osteogenic differentiation. Another thing is from my work is that hydrogel is a biocompatible material that is very close to ECM chemistry, but there is a lack of hydrogel to modulate cell ECM interaction at molecular level. To achieve that, we engineered the magnetic property into a hydrogel which exhibits low cytotoxicity. So in this work, we harness a bulk matrix as a physical barrier to conceal the RGD under the downward magnetic attraction, or a physical presenter to expose the ligand with outward magnetic attraction. So therefore, the switching between the adhesive and low adhesive can empower the differentiation potential of stem cell by reserving its cell stemness. Moreover, our work also shows that this platform can use directional magnetic attraction to induce the cell migration to the desired location. That is very useful for wound healing. Next, we are shifting our interest to light control because the lights have high resolution to trigger the precise scale. But no biomaterial can achieve a complex conformational changes that emulates the in vivo situation, especially by light control. So in this work, we engineer a photoresponsive protein to reversibly switch the tether length below or above the threshold for the activation of receptor signalings. So in other words, the breakthrough of this work is the ability to orthogonally print the cell phenotypes of the attached cells of interest before constructing the whole organs. So after we have gone through different functional platforms, we are also interested in how cells sense the microenvironment. We noticed that cells prefer to attach to long and isotropic material, but not too many studies explore this field. So we synthesize an array of anisotropic RGD-bearing gonadal rocks with various aspect ratio that can mimic the collagen and investigate how cell responds to them. So very strikingly, we found that even the strand fiber align to the high aspect ratio body with recruiting the diverse beta class integrin for the binding and alignment. So thereby it can promote the mechanosensing and the related cell adhesion and differentiation in vitro and also in vivo. And also we are the first reports to visualize this dynamic process through the high resolution SEM. So in summary, for the mechanomedicine, the mechanical cues are fast and effective way to regulate cell phase, and we can use different platforms to modulate the cell signaling through changing the amplitude of force transmission to the cell receptors by different stimulation. So these platforms allow us to study the molecular mechanism of disease origins and can be very useful for inventing therapeutic targets. So my second research field focused on developing biosensor based on the global pandemic of COVID-19, and we urgently need the new methods to rapidly and sensitively screen the potential patients because the conventional PCR is time-consuming and require intensive labor work that can cause the economical and social burden if the screening scale is really large. So the solution will be the application of the nanomaterial that can provide unique properties for constructing a rapid and sensitive biosensor to detect the viruses. So for instance, the gold nanoparticle can induce local electromagnetic field that can enhance the magnetic field close to its surface. Therefore, it can create a concentrated near field, so-called hotspot, to amplify the Raman signal. But the traditional sandwiching method is not suitable for detecting the long-chain nucleic acid, such as the SARS-CoV-2 gene. So in this work, we report a magnetic responsive source-based platform that can tune the strength of SEM, the source hotspot after detecting the target that can improve the limit of detection from 1 femtomolar to 100 attomolar. We also expand our interest to CRISPR-Cas protein as it is effective machinery to perform the DNA-RNA cleavage. So combining CRISPR-Cas with optical techniques has become prevalent for biosensing. However, the nanomaterial can impose a very large steric hindrance to restrict the performance of CRISPR-Cas. To resolve this limitation, we introduce a specially designed chimeric DNA-RNA hairpin that can be cleaved by the activated CRISPR-Cas12a, and subsequently it can liberate a large amount of RNA to disassemble this nanocluster and can drastically decrease the search signals. Therefore, it is a very effective on-off biosensor. and the level of the limit of detection can attain 1 attomolar. That is very close to the qPCR level. So in summary, to address the large-scale nucleic acid screening like the current pandemic, it is critical to build a fast and sensitive and also selective biosensor, which should have comparable sensitivity to qPCR and can also reduce the overall economical burden. And we expect the next generation biosensor can achieve the multiplex targeting to save cost and time. So in overall, my current academic performance can be summarized by 8 first or co-first offered, as well as 7 corresponding articles. I also pursue several grounds to support the academic research as a co-I and PI at PolyU, and several articles of my work have been promoted by different WeChat subscription and also university news. So this is the end of my presentation. Thank you so much for your attention and time. Q&A session is now open. Thank you.